their ability to desorb things from the surface, changing the surface, putting things into the gas phase, and maybe trying to make a connection between the plasma observations, the gas phase observations, and the surface observations. Of course, the surfaces are complicated. They're not like lab surfaces, right? They're grains that are with a high porosity surface that things can be absorbed and desorbed. So it's a complicated problem. I guess that's good because I can do it for a long time. Anyway, we know a lot about Europa. In Europa, it's pretty interesting compared to some places, at least in the distant solar system. We know the plasma flux coming in roughly. We know the radiolysis it may do. There's been nice lab measurements to show how when you implant sulfur and you then irradiate it, how you have a sulfur cycle and also a carbon cycle. It contains salts and organics, and those have been identified. And things in the gas phase have been identified, so there is some coupling here that's we've actually been able to do. A lot less than we'd like. But today I'm going to just focus on first sodium, and then oxygen, and then the reason Abby invited me, she heard my talk at the MOPE conference in Uppsala and wanted me to say something about desorptions of organics by plasma. I'll say a few words about it at the end, but haven't done much since then, so if you were there. Anyway, so focusing on these, I want to remind you, some guy named Brown saw sodium, ambient sodium around Europa, and luckily Francois Leblanc was a postdoc at my place at the time and was interested in modeling that. And later on, Potter made some additional measurements, and we put these together with simulations by Francois. And I'm telling you this because it's sort of a success. That is, sodium in water ice is sodium plus typically, okay? And what the lab people did, Yashinsky and Mady, and unfortunately Ted Mady died early, not so long ago, they showed that electronic desorption of sodium in the ice, adsorbed in the ice, was the proper way to get sodium into the gas phase. Not the proper way, a way to get sodium in the gas phase. And that could be whether it's ions, electrons, or photons, okay? And what happens, of course, is if it's plus in the ice, it's closer to the water molecules, but then what the radiation does is excite an electron, and the electron can get onto the sodium, and so now it's mounted in an orbit, but it's too close to the water, so it repels and goes off the surface. So they were nicely able to get not only the yields as a function of photon energy and electron energy, but also the velocity distributions of the ejecta. Very nice experiments, and that were very helpful. And therefore, Francois took that with Mike's and the Potter observations, and had this picture where the plasma might eject sodium from the trailing hemisphere, okay? And that would happen all during its orbit. And that's sodium because the plasma also can directly sputter. It might not only be the process I talked about then, but could just be a general ejection process. But in addition, the UV photons illuminating it would also drive things as Yashinsky and Mady showed into space, okay? So putting those together, we got the model that was showed in the previous slide, and we're able to get something that looked like a good correlation between the observations and the lab data and the modeling. And so that was, I think, a nice success. And what we learned then, of course, is the sodium production rate and loss rate. And that made it clear that the sodium was endogenic. It was thought to be endogenic because there was also information about potassium. And so the potassium and sodium ratio were different from IO, but when you have the possibility of some sodium ions coming in from Io. It wasn't clear in those days, and now it's clear. If you did the same thing with sulfur, it's clear that you don't have the ocean. There's plenty of sulfur being deposited in the surface and being recycled to explain everything that's seen so far. And the same with carbon, and in fact there's not much carbon in the plasma that's coming from Io, okay? So these seem to be some success, getting a picture here. So the question then is, what about O2? O2 was one of the first things observed in the gas phase, and it's also seen trapped in the ice. And therefore, we should be able to do something similar. Its ultimate source is the plasma. Laboratory data, I'll show you in a minute, confirm that. Okay? And so we'll model similar for the Na model, work for O2 with only plasma production of the thing. Because when you drive sodium into space and it returns to the surface, it adsorbs and binds, okay? O2 into space comes down, and if the temperatures are right and the ice is at the temperatures we think it doesn't adsorb, okay? And so it needs to be ionized or dissociated to be removed or something like that. Okay, so that's the picture. And the data, I put this in here because I always like to give Walter Brown credit for starting these experiments in Lou Lanzarote. And then I realized this is 36 years ago. Okay. Sorry, we haven't made more progress. Okay. But it's amazing data, and Ben Tielos and Ujwa Root and others have just elaborated on it beautifully. What you find when you start irradiating something, it doesn't matter whether it's photons, electrons, or ions. You drive off some hydrogen immediately. Sorry, in the lab they use D2O ice for obvious reasons. You drive off hydrogen immediately, and therefore you now have an oxidized material. And as you drive more off, you start having the possibility of forming O2. Forming O2 directly in the gas phase is difficult, the old McElroy or Young and McElroy model. But in ice, because it's trapped there and stays there, it works pretty well, okay? And so finally you have a dose dependence. and so you eventually make O2. And the O2 you make is temperature dependent. I just chose an electron induced process from the Georgia Tech people, okay? And it's temperature dependent. Don't worry about what's going on here. The temperature's gotten too high and the ice is sublimating away. Okay, and it also is done by photons. So preferential loss of the hydrogen, which doesn't adsorb at these temperatures in the ice, okay, leads to the production of O2. And there's a nice paper by Ben if you want to get all the details, up-to-date data. However, Tim Cassidy has looked at all the models and the lab data, particularly the models for the plasma, and found that, wow, order of magnitudes differences here, okay? So there's a lot of uncertainty in what the plasma is doing, okay? And Ben and Tim pointed out that, okay, that dose dependence is important. That means when the moon's surface changes temperatures, you don't immediately get the O2 yield that is measured in the lab at that temperature, because it takes time to adjust to the temperature, okay, and build up the right amount of oxygen versus hydrogen in the lattice. Okay, so with those caveats though, we still wanted to see, I first want to say, getting an order of magnitude estimate was pretty easy based on Walter Brown's 1982 experiments. We made an estimate, and the estimate was, I guess, a little bit robust because the plasma is producing the O2, but the plasma is also destroying the O2. So it's a little bit insensitive. And okay, things have changed. Maybe there's lots of observations and estimates based on modeling that they're within an order of magnitude each other, which, hey, this is planetary science, so that's not bad. Okay, and the reason it's a little insensitive, even though the first experiments were pretty fresh and new, and we didn't know a lot about the plasma at that time, is because there's some level of insensitivity to them. Okay, well, so Francois had a student from Virginia, Apurba Oza, and Carl Schmidt, who was a postdoc at Virginia, and they went there and they decided to do the same thing they did for the sodium thing, but for oxygen. A nice model, lots of data, they thought they'd do it. They made a surface temperature map based on albedos. You can argue about how accurate it was, but it's pretty good. A plasma source of O2, both with and without the temperature dependence. Okay? Thermal absorption and desorption of the O2 when it comes to the surface. Okay? Diffuses hopping of O2 across the surface once you produce it, because unlike the sodium, when it lands on the surface, it doesn't go into a binding site right away. Okay? Reactions with the surface, they allowed as possibility. They also put in the Coriolis forces. Okay? And then the big problem, and that's why I asked the question the other day, is we don't know a lot about the ionization and excitation rates really close to the surface of Europa. The sodium atmosphere was extended. This has a scale height that's fairly close to the surface, so you really have to know what the electron impact. So they chose all this accuracy, chose an average estimate of that. Okay? Okay, and here's the kind of thing they were able to model. The color indicates the O2, focus on the stuff close to the surface. They also did the dissociated O that went farther away. I'm not going to talk about that today. And what they always noticed, is that there was a bulge at dusk. Okay, that's great. Comparing to data to observation is hard. A bulge at dusk was seen. Okay. But their simulations didn't do a very good job. They did the work, but we call them our simulations. Okay. Some places it was right. The dark points are the data from Roth. Okay. These are quadrant averages of what you see, taking the dusk quadrant and the dawn quadrant and ratioing them. And it didn't change very much with sub-observer longitude. This would be looking at the trailing hemisphere. This is the leading hemisphere. But their model was very different in some places. Order of magnitude, okay? Well, you can fix that. We don't know the ionization rate and emission rates, and Roth has warned everyone about the emission rates may not be directly related to the column density or simply related to the column density. They may not be proportional. You got to be careful. But ignoring that, because of their paper even, they also compared it to column density estimates. Okay, with those caveats, we thought, okay, well, maybe you can adjust it, fix the albedos, fix the emission rates, fix all these things, and you can probably get what you want. But we decided on a different approach. Too many things in this model, let's simplify it. Okay, actually, the dawn-dusk ratio was pretty simple. Okay, so we did an analytic model. No hopping across the surface. That's not so good because they actually diffuse about a third of the way across the surface or 1/6 of the way across the surface before they're ionized. But let's throw it out anyway, okay? No Coriolis, no centrifugal effects. And let's average over latitude, because they already showed us that if the dipole tilt is one way or the other way, things go from north to south. Okay? Calculate the column density then only with sources and loss processes. There'll also be ionization and dissociation. But now let's try solar insolation only. Okay? Because this O2 production has been going on for ages, the material is porous. And one of the big questions, of course, is in the astrobiology idea is, can you get that O2 into the ocean? Well, before you can do that, you better get it into the regolith somehow, okay? So if you imagine a regolith that's permeated with O2, maybe the solar effect is interesting. And we wanted to compare that with analytic models of the trailing and leaning hemisphere and all the standard things people have done. Okay? And so a key parameter in this, obviously, is this thing that's a little uncertain, the loss rate, compared to the angular speed. That means how long do the O2 survive as Europa is rotating around. Okay, so with the kind of thing you'd get an atmosphere with solar insolation, and you can decide whether it's thermal or whether it's UV driven like sodium. Don't want to argue about that. There's something would peak at noon and go down. And if you just put that into column density production for a fixed loss rate, okay, what you do find is the column density are the dashed lines for two different values of that beta, which is the orbital speed compared to the lifetime, okay, to the ionization rate. You, of course, get a Dusk enhancement. You know, that's been known at the moon or other places, right? And so this simple model does give a Dusk enhancement also. It's better, there's rotation, okay? And if you compare that, though, as a function of subobserver longer to the data, it's also independent of subobserver longitude. Okay, that may be lucky. We don't know, okay? And it not so different whether you have two different values of the loss rate that have been in the literature, okay? So, but of course, if solar radiation can drive off O2, the plasma must also be able to drive it off, okay? So it's an amount. We're saying, oh, there's a suggestion here that the effect is predominantly driven by the sun. I would hardly say we proved it, okay? But it's an idea. So then you look at other things that Roth did, which was take and ignore the blue. We're using O2, we're using the 1356 as a proxy for the O2 line. He integrated, because of course the fact that the plasma is going up and down, he integrated the brightness over the disk and out from the disk. And notice that what you see is the leading and trailing hemispheres aren't so different, right? So actually there's a slight enhancement on the trailing hemisphere. Oh, maybe that's the plasma effect, I don't know. But of course you also notice that the scale height here is not the thermal scale height. And if you just take a simple scale height atmosphere and put it in, Roth has shown that you get really problems in here. So hey, having this as two pieces might not be so bad, with a large piece that's thermally driven and a piece that's produced by the plasma. But there's work to be done. We made some estimate on what the desorption energy might be and things like that. Okay? Oh, but this is a model. There's reality. Okay? There is no simple global uniform atmosphere. Okay, well, we didn't have a uniform atmosphere, and you can see the north-south differences that Roth discussed beautifully, and leading trailing hemisphere differences. But there was always a Dusk enhancement, and so our averaging over latitude was useful. And of course, this must have something to do with the local surface properties, right? I mean, it's got to be not only the plasma, but the local surface properties. Oh, or if you're putting gas into the atmosphere, that affects the electrons that are coming in. So there could be some feedback process here. So it's going to be much more complicated than we show, but if we have shown, and maybe we have to do more work, that the sun is important for this, that's been totally ignored up till now, except as affecting the plasma sputtering units. Okay, so there's a lot of work to be done here. We immediately, when we saw this, thought, and then saw the paper by our two colleagues here, we thought, oh, maybe we could find some of those spots and match things up. And when I was doing that and wasting my time, Carl Schmidt wrote me, you think they would have published that without doing that themselves? So they would have noticed immediately. So no, we don't see, but the properties vary considerably. It could be thermal inertia or thermal emissivity, as we showed. Then they also, these people also showed that you get an aurora when it's an eclipse. Well, that's not too surprising because there is, of course, an aurora and eclipse because the oxygen stays in the atmosphere for a while, takes time to be dissociated, and during that time it could be emitted because you've only shut off the sunlight. Oh, but maybe if you shut off the sunlight for a while, we can separate what part is plasma and what part is solar driven. Maybe. Okay? Okay. So we'd like to know what is the state, we'd like to think more about what is the state of O2 in the surface. This is something that Ben has talked about in some of his papers, but we seem to think now, and he's talked about binding of the O2 to dangling hydrogen bonds that would be produced by the radiation. So we're using that in our discussion as a way of thinking about it. But it's clear something is happening, to me at least, that is affected by the sunlight. So, oops, that was the wrong one again. I know why people do this all the time, okay? But maybe we can turn this around eventually if we pin this down and say something about the surface properties. Because you're talking about emissivity, you're talking about thermal inertia. Well, if you're putting things into the gas phase from something that's permeated with oxygen, that's another way, that's another kind of emission, right? And so it may tell you something about the surface properties. Or is all that stuff that we see, that spatial variability, is it all just due to the plasma people? Well, they'll let us know at some point, okay? Anyway, so there's work to be done. And now I'll just switch here, if you don't mind, to what Abby asked me to talk about briefly, is the sputtering of large organic molecules with Na, O2, large organic molecules, okay? So I'm not worried about killing these things off. You can alter them, you can do a lot of things to them, but I do know the laboratory data has shown us something else that I think is important. There will be some kind of organic materials. How well we're able to interpret this, I don't know. That will be on the surface. Can we identify them by the heavy ion sputtering? Everything up to now didn't have anything to do with the energy of the ions in particularly, but this does, okay? When you put in heavy sulfur ions as part of the plasma, you can absorb large numbers of water molecules, okay? The lab data that I worked with when I was going to Uppsala with Bo Sundquist and those people have shown that you can always eject with a heavy ion large intact biomolecules. Okay? So therefore, it's possible that the sputter ejection contains large organic molecules. The only problem is all this stuff was done with idea towards medical applications, and so it was never, except one or two cases, done organics in water ice. There was pure organic samples, there was organics in various kind of matrices, but unfortunately not in water ice at the relevant temperature. So there's a need for these experiments. Okay, and this comes about, I just want to remind you, the other aspect of Brown's data, which again, Ben has summarized all this data together nicely. When you talk about a heavy ion, a fast heavy ion now. And these down here may be the predominant ions, but there's enough of these, and when they eject stuff, they eject thousands of molecules. And this is oxygen. Okay, this is the 1983 data. Ancient history. Okay, so Tim Cassidy, again, has summarized a lot of this stuff. And so we have the various kind of things. Protons have an average mass ejection of 24. Oxygen, if you average it over the fluxes and the rates that people think, the average mass ejected in terms of water molecules only is 230 AMU. And you get sulfur on the average from low to high is 2,000 or so water molecules per ejecta into the system. And if you focus, as Tim did, on the greater than 50 keV ions, you can get 18,000 AMU per ion ejection. If there's an organic molecule in that stuff, leucine and thing, I'm sure you can get it into space. Okay? Just to remind you, because it's not a literature most of you know, there's a huge amount of work on ejection of proteins and amino acids and other material that all done because of medical analysis issues. And you see that you have, with the time of flight spectra, you can see that you have sharp peaks, ion peaks, where the large molecules exist, even though you're ejecting massive amount of materials. And what's happening, we think, is that, of course, when an ion goes in, it destroys all the material it goes by close to, okay? But it also expands the electron cloud and produces, just like the sodium atom thing on a smaller scale, a large pressure pulse. It goes through the material, and so what you can eject, and this is an experiment they did for fun, buckyballs. Okay, so it's possible when you have these large, heavy, energetic ions coming in to eject material. Okay, so what are the conclusions? Okay, if the ocean material containing organics reaches the surface, there will be intact biomolecules in the ambient plasma. I'm telling you that, okay? You don't have to believe me. Okay? Because we know this stuff is coming in. We know these sulfur ions, MEV sulfur ions are pouring in there, right? I mean, there's no way. Now, if there's nothing on the surface, nothing will happen, okay? So we might look for amino acids and lipids correlate with features. I made a crude estimate. I'm sure this is totally incorrect with these people here. We're using the organic mass in the water. Oh, sorry. Too much coffee. Okay. It doesn't matter. If using the organics in the Earth's ocean about what you would see in the gas phase, okay? And they may come out as neutral, they may come out as ions, but you have these low energy electrons around, so there'd immediately be electron attachment on these big things. And so you should be able to see them in the plasma. By the way, if you don't see them in the plasma, I don't know about your other designs for spacecraft. You know, it may, you have to see it in the plasma, I think. Okay, attachment, what am I doing? Okay. And so we need experiments on biomolecules and ice to prove this. The detection and identification of individual ions is challenging, but there's some new instruments on the way that look like they may be able to do this with large molecules. Oh, as Roger pointed out, they've seen big organics in the space, but the mass resolution hasn't been such that you can do it, so you need something with mass resolution. Okay? Okay, so because this is mostly a laboratory session, I want to remind you that Hans Alfvén, a lot of this work was done in Lupton, always said, I always believe that astrophysics should be extrapolation of laboratory physics. But you remember, he was dealing with atoms and molecules. It's hard, especially, geology. I listen, I try and understand, but okay. Okay, but if biomolecules can reach the surface, they will be detected in the plasma. That's my prediction, okay? Thank you very much. Yeah?
Oh, we gotta do the mics.
Oh, by the way, I see
okay.
who's standing up here. Yeah, I forgot. I saw the poster. I think one of the slides, I think, had it on that energetic dust comes in.
Also will release.
Yeah, and it
particles,
would
yes. We'll compete
dissolve
with this, yes.
much more, but you'd see it in the plasma.
You will say. So my question is really, thank you for the nice overview, is that are you saying that those micromolecules or macromolecules will come off as ions, or that the ionization stage is going to depend on the matrix?
The ionization state will surely depend upon the mixture, and you guys are doing experiments on that, I know. But so some will come off as ions. In the laboratory, simple laboratory experiments, when you're doing medical labs, they always look for the ion. But we know from the modeling that a large fraction comes off as neutrals. But these neutrals are dumped into this low energy electron, high density, low energy electron environment, and there'll be attachment pretty quickly.
And they can come up as negative or positive
Yeah,
ions.
and so you have to do negative and positive.